Okay, let's continue. And I hope all of you have finished the homeworks. And the second lesson is corresponding to the class on the last Friday. Okay, and last time we talked about if you got the distributed loadings, and the last lecture we emphasized on if the applied loadings, which is applied to the entire boundary of the elements, and remember we use the mapping and the inverse mapping to describe the geometry of the structure. So the best way you consider the applied loading, you consider the applied loading which is applied to the entire boundary of the element. So for this case, it is the entire range. So you can very easy to specify the boundaries you like to consider, just like in your homework for this one, which is the c equal to 1, and the eta is changed from the -1 to +1. Okay, so that's the boundaries we like to consider. So it's very easy, and when you need to integrate the work done by the external load, so you need to specify the range of the remember the range which is specified in the masked element, not in the real element. It is easier to specify the range in the masked element than specified here. Okay, so that's the range. And in the real element, the ds is equal to the dx squared plus dy squared, and then take a square root, then we can get the ds. And for this one, it can be changed. Okay, so the ds can be changed like this one, and so we can multiply this term to the d eta, then we can get the ds, and the ds it is the resultant applied at ds. Okay, so we need to multiply the w to the ds, then we can get the resultant load, which is obtained from the distributed loading w multiplied by the ds. So we can always multiply the 1/2 uv. The u and the v, they are functions of the eta. So the uv, they are not a constant. They are functions of the locations we considered. And right now, it is a very special case if we consider one of the boundary lines. then we just consider the u and the v functions at this point. So the u, they are c equal to 1, the eta, and also v, which is and that which is the summations ui okay. If we specify the c is equal to 1, then you will find the shape functions of all the nodes which is not lie on the considered boundaries. The phi functions value, they will be all equal to zeros. Okay, so only the node points lie on the considered boundaries. We have the non-zero phi functions. Okay, so sometimes you don't need to consider all the node points. If you know you are considering the boundary, let's say that's the second boundary line. If you consider only the second boundary line, you can simplify the nodal displacement. You can put only the nodal points along the second boundary line multiplied by the corresponding phi value. Since we have specified the c equal to 1, then actually they are the interpolation functions only related to the eta. Okay, so that's you can simplify. Originally, you can simplify the ui, also the phi functions we need to consider. Okay, so if we know the c and the eta, right now we know the c, but the eta is still a variable. The eta is still a variable. So as long as you know the eta, you can calculate the corresponding u and the v value. Okay, no, for the considered thing. So that's the integration variables eta. The eta needs to change from the -1 to +1 in order to calculate the work done by the applied loadings, and also the work when we calculate the work done by the applied loading. Also, we need to consider the corresponding displacement of this boundary line. Okay, so that's the basic formula, and also you need to remember how do we calculate the integrations. We will change it to the numerical integrations. For example, if you consider the two nodal points along the boundary, or it is the three nodal points along the boundaries. For these two cases, you can use only the 2-point integrations, and so the j is equal to 1 to 2 or some other. It depends on how many nodal points you use along the boundaries. For most cases, it is enough to use the two-point integrations. So although it is an integration, the eta is changed continuously from the -1 to +1. Also, we need to consider the eta in an infinitely small d eta. But in the numerical integrations, we just calculate the function values at the integration points. If we use the 2-point integrations, there are only 2 integration points we need to consider. And I think most of you can remember these 2 points. They are the -square root of 1/3 and the +square root of 1/3. Only 2 points we need to calculate the function values. Okay, so you can calculate you can calculate the function value. Right now, the function value includes the u and the v, and the u and the v, they are still related to the considered eta. So you need to replace the eta of the integration points. For example, the negative square root of 1/3. You need to replace the eta to calculate the corresponding u, and also you need to replace the eta by the for example, the negative square root of 1/3 to calculate the v. So the u and the v, they are functions of the c and the eta. Right now, the important thing, the important parameter should be the eta, not the c. C is known always equal to +1. Okay, so you need to calculate the uv function of the integration points. And also, the other term which is also related to the coordinates of the integration points, they are this square root. Okay, since the x Okay, so the x, they are, we can calculate the x by the summation of the nodal coordinates xi multiplied by the phi. Again, right now, if we consider the second boundary line, only the nodal points on this boundary line will have the non-zero values. The other nodal points, they all the phi values, they are equal to zeros. Then if you replace c equal to 1, then you can check the corresponding results. Okay, so that's the x. But when we calculate this square root, we need to calculate the partial x to partial eta. Okay, since the xi, they are the known constants, and they are not functions of the c and the eta at all. So you don't need to take partial derivative to the xi. But the phi, it is functions of the c and the eta. So and also the phi, all the phi functions, they are the known functions. So you can calculate the partial phi to partial eta. Okay, we can take the partial derivative to the known functions, and the calculated results, they are all also the known functions. And these known functions, they are still functions of the c and the eta. And for these problems, they are only functions of the eta. So for these two terms, they are still function of the eta. So we need to replace the corresponding eta values for the integration points to calculate this term. Okay, so for this part, they are the function values at the integration points. That's the part you need to calculate for your homework problems. And then we need to multiply the weight of these integration points. And for the 2-point rule, the W1 and the W2 both equal to 1. But for some other integration rule, you need to check the table to find the corresponding W and the correspond to the corresponding integration points. Okay, so after you calculate this, you can calculate the W, and then you can get something which is the okay. I use the small p vector, and right now the U transpose, they are the most of the time we will say the U transpose vector. The U vector is the nodal displacement of this element. If you use the 4-node element, then the U vector will include 8 elements. It will be the U1 V1, U2 V2, U3 V3, U4 V4, and there are 2 nodal displacements for each nodal point. So if you use the 4-node element, the total number of the elements in the U vector, it will be equal to 8. But if you use the simplified form, then you can say the nodal displacement we need to consider only the 4 elements related to these 2 nodal points. Okay, but when you consider the equivalent nodal load vector, you had better consider the entire the complete displacement vector. So it means we have 8 elements in this vector. Under the p vector, they are the so-called the equivalent nodal loads. So it means if we multiply the nodal displacement of this element by the equivalent nodal load vector p, then you can get the same value of the work done by the distributed loadings. And that's the part you need to finish in your homework. So you can get the 4x1 vector or 8x1. Okay, if you consider the convenience to assemble the local load vector to the global load vector, then you will find it is convenient to use the vector, use the 8 elements. So even the 4 elements for these 2 nodal points, they are all equal to zeros, but you can still keep these 4. Okay, so that's the part you need to consider. Then let's consider the second case of the distributed loading. And right now we are considering the distributed loadings. They are applied on a curved line. Okay, the curved line, the first part, the curved line, which is exactly one of the boundary lines. And the second case, let's consider the okay, that's the case we are going to discuss right now. And for this case, the curved line is not one of the boundary lines. The curved line is inside an element. Okay, so that's the case we are going to consider. So that's the case. the case we are going to discuss is the distributed load which is applied on a curve line. Rather, this curve line is inside an element, not the boundary lines. Okay, and then the user needs to input first. He needs to input the Wx, Wy, and then you can ask the user how can a user describe this curve line, and you can ask the user to input that's the distributed loading. That's the Wx and Wy. They are the magnitude of the density of the applied loadings. And for the Wx and the Wy, we need to multiply the length. Then we can get the resultant load at a small region. And that's the first part. And the Wx is the component of the distributed load along the x direction. The Wy is the distributed load along the y direction. And then you can think, how can we ask the user to describe the curve line? Okay, so one of the method, we can ask the user to describe first the two endpoints and one middle point. Okay, we can ask the user to input the two endpoints of the curve line. Also, one is the other one is the middle point. Okay, so since the user needs to define the global coordinates. The global coordinates, they are defined by the program user. He can decide where is the origin of the coordinate system, and also he can decide whether the x-axis is along the horizontal direction, the y-axis is the vertical direction, or if he like, he can say the x-axis, which is 30 degrees from the horizontal. Then the y-axis, it will be the 120 degrees from the horizontal. Either one, it is okay for the program, as long as the user he decide where is the origin and the orientation of the x and y axis. Anything will be okay. And the xy coordinates, they are defined by the program user. So the program user, he is familiar with what is the xy and the xy axis. And if the program likes to ask the user to input something related to the locations of the points, the program had better ask the user to use the xy coordinates. And we know there is another set of the coordinates, which is the c and the eta. But the c and the eta axis, they are used in the masked element. And for most program user, they are not so clear about what is the c and the eta. but the user, he knows very clear what is the x and y axis, since the x and y axis, they are defined by themselves. So he knows these two very well. But if you are telling him the mass element c and eta for a very well-trained program user, probably he can do this. But for most common users, it is not so easy to ask the user to input the c and eta values. So most of the time, the program will ask the user to input for these three. That's the 1, that's the 2, that's the 3. So the point 1 is the end point. That's the middle point. Okay, that's the second end point. Okay, so that's the data the user needs to input to tell the program where is the curve line, what is the applied loading of this loading case. Okay, so after the program receive the input data, also remember the nodal coordinates of this element. They are also the known values. Okay, we know all of these, the nodal coordinates for all the related nodal points for this element. This time I draw a 9-node element. Okay, so remember, you can choose the 4-node element or 9-node element. It depends on the accuracy you like to get, and also it depends on the calculation time you need to spend to get the results. Okay, so but no matter this element is a 4-node element or 9-node element, for both cases, you can get complete information about the related x and y values for all the nodal points. You can always get all of these. Okay, so on this page, you know, so you can understand what kind of the information we can get from the program user. Okay, you can print the screen. So I'm going to erase. Okay, after we get all of these. So remember in the last week, last lesson, and the lesson one, means the first online course. The first lesson in my idea, it is corresponding to the class on May 17th. Remember on the May 17th in the night we have the class, and the lesson 2 is going to be the May 22nd. So the lesson 2, which is the May 22nd class. Okay, so in the previous lesson, if we know the xy, how do we find if we know the real coordinate xy, And most of the time when we use this type of the technique, the consider the point which it is not one of the nodal points. If if you like to find the xy, the easiest problems will be that's the first node of this element. Okay, so we know the first node will be mapped to the first node in the mass element. So these node points will be the c and eta. They will be both equal to -1. Okay, since we know this node point is mapped to the first node point in the mass element, and for all these related nodal points, it is relatively very easy to find the corresponding c and eta. But if the x and y, which is inside the element, we know the range of the c and eta. The c, which is in the range from the -1 to +1. Also, the eta is from -1 to +1. But if we know the x and y, how can we find the corresponding c and eta? The first method, if you can solve the inverse functions, which is the c equal to some x and y, you can get, if you know the xy, you can get the c and eta. But to solve the inverse functions, it is not so common, since for some problems it is not so easy to find the inverse functions. But we can use the trial and error procedure. We can use a series of the trial and error procedure. Let's try the first try. Probably the first try of the c eta, we will use the 0 and the 0, and the 0 and the 0 point, which is just the center point of the mass element, and then we can calculate the Jacobi matrix and multiply by the delta c and the delta eta, which is equal to the delta x and the delta y. Okay, since we know the target x and y value, that's the locations we like to find the corresponding c and eta. But we don't know the c and eta. That's the trial value. You cannot expect in the first try you can get. But if we know the c and eta, then we can calculate the corresponding If we know the c and eta, also we know all the nodal coordinates of this element. So if you know the c and eta, you can always calculate the corresponding x and y. We know the target xy. We know the trial, the xy corresponding to the trial values of the c and eta. Then we can calculate the delta x and the delta y. Okay, so that's the deficit of between the trial values of the c and eta and the target x and y. So we can calculate the delta x and delta y from these two formulas, also the input xy values. Also, we can calculate the Jacobi matrix on the trial values of the c and eta. So we know this part, we know this vector delta x and the delta y we know the Jacobi matrix. It is a 2x2 matrix. And if we know the Gaussian eta, then we can calculate the Jacobi matrix. Then we can use the program to solve the simultaneous equations. Then we can get the data Gaussian, the data eta vector. So the second try will be the okay, so we can use the solve the data Gaussian, the data eta to get a modified Gaussian eta. So we will expect the next trial values will be better than the first trial value. Okay, so after several iterations, so you can get a set of approximate Gaussian eta. And remember, the finite element method is only a numerical method. You should not expect anything which is exactly same or exactly. So it is not so important to get the exact values of the Gaussian eta. But you can always get a set of approximate Gaussian eta. But those approximate values, they are close enough for most requirements in our calculations. Okay, so we can do this. Use the for the known x and y, find the corresponding Gaussian eta. Okay, so take a picture, then I will continue. Okay, so if we know for a set of the known x, y, we can always find corresponding Gaussian eta. So for these problems, we have 3 points. We have three points: x1, y1, x2, y2. We have the okay, remember how do we define this curved line? We can ask the user to input the xy coordinates of 2 endpoints, also one of the the middle point of the curved line. So these 3 sets of the xy coordinates, they are input from the user, and we can repeat the procedure. Use the trial and error procedure to find the corresponding Gaussian eta. If we got the 3 points, we just repeat it 3 times, so we can get the 3 sets of the Gaussian eta corresponding to these 3. And let me draw the mass element. And right now we can find the 3. Okay, so we can find the 3 points in the mass element, and we know the loads Wx and the Wy, they are applied to this one. Again, we can calculate okay, so we can still use the integration formula to calculate the work done by the applied loadings. That's the UV, but all these, the ds, they should be the length in the real element. So the ds will be the length in the xy plane. Okay, so if we can multiply the ds in the xy plane by the distributed loading wx and wy, then we can get the resultant load along x direction, along the y direction. And for these two resultant loadings, they should be multiplied by the u and the v, and the corresponding x displacement along the x direction, the displacement along the y direction. Then we can get the work done by these loadings. But right now the curved line is mapped to a curved line connected by the 3 points, and the c and eta, both of for both parameters, they could be changed. It is not a boundary line. Okay, the distributed loading is applied to this, and it is not so easy to describe. And also remember, later we will integrate. We like to integrate over the curved line. And for the variable c and eta value, it is not so easy to integrate. Remember, for the Gaussian quadrature method, the domain considered must be the -1 to +1. Okay, I think it is the time. I'm going to take a break, and I'm going to continue to the next hour to solve this problem.